In this video, we're going to learn about the concept of linear combination and spanning sets. And so what that is we are going to take vectors and combine them in a linear fashion. So that's why we call it a linear combination. In particular, what we mean by that is that if you have some vectors, we'll call them v1 through vn. A linear combination is anything you get as a result from calculating constant times vector plus constant times vector plus constant times vector and so on. If you combine them all together, whatever answer you get is considered a linear combination. So as a quick example here, we have v1 and v2 in our R2 vector space here. And if I did, for example, 5 times v1 plus 2 times v2, that'd be 5 times 2, 3, plus 2 times 5, negative 1, is 10, 15, plus 10, negative 2, and we'd get 20, 13. So that right there is an example of a linear combination of v1 and v2. And you can pick your numbers, your constants, to be whatever you feel like. So in this case, I did 5v1 and 3v2, but there was no reason I had to pick those. I could have picked any other numbers. And in fact, you might even think this is cheating, but it's not. You could do 1 times v1 plus 0 times v2 would be 1 times 2, 3, plus 0 times 5, negative 1. And surprise, surprise, it's going to give you 2, 3. That would also be considered a linear combination of v1 and v2. So again, for linear combination, you can have any constants whatsoever involved, and you just put a constant from one vector, constant next vector, add them all up, and that's called a linear combination. Now, a more interesting question is going to be whether a particular vector is a linear combination of these ones. Is there some way to combine them together and get the answer 1, 10? And so if we want to do this, if we want to be able to get this answer here, one way to do that is to say c1 times 2, 3 plus c2 times 5, negative 1, and see what the answer, if it's ever 1, 10. And then basically we have equations that we want to solve here. So we would say 2c1 plus 5c2 is going to give me 1, and 3c1 minus 1c2 is going to give me 10. If you want to put that in matrix format, it's going to look like the following here. And you kind of can see there your v1 is your first column, your v2 is your second column, and then the answer is the right column. Regardless, you can solve this here, and what you should get is c1 is 3, and c2 is negative 1. And we can just quickly check here, 3 times 2, 3, plus a negative 1 times 5, negative 1, and that should give me 1, 10. So because I found specific numbers that showed we got the answer 1, 10, then yes, it is a linear combination. So we just proved that that specific vector 1, 10 is a linear combination. And there's a graphical idea here. The graphical idea is you have your two vectors you started with, and the question is, can you combine them in some way to get to the vector 1, 10? And we just found that there was a way to combine them to get to that. Can we actually, reach that point? But the more important question in a class like this is going to be not can we just reach that one point, is can we reach every point in our vector space? Right? Can we reach over here, and can I reach over there? And so can I reach every single one? And that is called a spanning set. So again, the definition for a spanning set is, can you reach every possible vector as an output using linear combinations. And at first, this is going to be somewhat tricky to determine yes or no, but later on, we are going to learn some shortcuts to get the answer faster. So let me first give you an example where it does work. 1, 0, and 0, 1. That is a spanning set. And the reason why is I need to ask myself, is any random vector a linear combination? And the answer is yes, because you can write the xy as x times 1, 0 plus y times 0, 1. So that shows you that xy is a linear combination of v1 and v2. And since x and y could have been any vector that we had, therefore the vectors v1 and v2 have to form a spanning set. Now, the second one, this question says, are these a spanning set? Well, if you look at it from a graphical point of view, 2, 3 is something like this, and 4, 6 is actually in the same direction, just twice as long. So if you're only allowed to travel in these two directions, can you get everywhere? No, you cannot. And you could just try, for example, 1, 0. And so you would check, can you have C1, 2, 3 plus C2, 4, 6? Will that ever give you the answer 1, 0? And it turns out there's going to be no solution, which means they are not a spanning set. I will leave the algebra of solving that up to you guys to see that I did it right. But in this case, it's not going to be a spanning set because the two vectors go in the same direction, which means you would not be able to reach anything that wasn't on this line right here. Now let's look at some more exotic vector spaces. Let's look at the set of all 2 by 2 matrices here. So 2 by 2 matrices, turns out that if you just put 1 in each corner, those 4 together will be a spanning set. And again, to verify that, you can take any random 2 by 2 matrix and write it down as a linear combination of these 4 matrices, or 3, 4 vectors. Right? And so therefore it is a linear combination, and since this was an arbitrary vector, it works. In fact, this is called like the standard spanning set. It's the normal one that you'd like to use. It's the most default one we have. We also have the case for, sorry, not R2 here, this should be P2 for the polynomials. I have x squared, x, and 1, and that's again because if I take any random quadratic polynomial here, I can write it as a times x squared plus b times x plus c times 1. In fact, I don't even have to write it out that way, it's already written in that format there. But that's a v1 plus b v2 plus c v3. And so once again, we've proven that any vector is a combination of these, which makes that a spanning set. So it's a very interesting situation. We want to look for these. We want to determine if something's a spanning set or not. As I said, right now, the only way to do that is to try to solve systems of equations here and see what happens. We are going to look at that and find better ways to answer the question, but we just haven't gotten to that point yet. And so this is the concept of a spanning set.